So basically nuclear was doing reasonably well in Asia. Altogether there were 65 projects under construction at the time of Fukushima. But even the nuclear construction activity that was ongoing just before Fukushima, you would need to increase that by a factor of 1.5. Now that is very, very difficult to imagine post Fukushima. And you are completely right. You are completely right that in nuclear, the biggest pressure by far is who will finance it. Because every single nuclear power plant which is operating today in planet Earth was built by either direct state investment or by state-regulated, vertically integrated monopolies. You know, the nuclear power plants were built in the 1970s, 1980s, the ones that are operating today. And in the 1970s and 1980s, there were no competitive electricity markets. So either nuclear was completely state-owned, or in the United States, for example, nuclear was not state-owned, but nuclear was built by vertically integrated regulated utilities who did not face any competition, whose prices were regulated by the government, and who would pass the cost of nuclear into the consumers.
How are they building the one in Finland now?
The Finnish project, the Finnish project is vertical integration, but it's a market-based vertical integration, because that's because the business model that they set up was that Finland has energy-intensive industry, especially the paper industry. And they set up a consortium of energy-intensive manufacturing companies. And the energy-intensive manufacturing companies bought into the equity of the nuclear project, and they also buy electricity from the project. So they eliminated the market risk from the nuclear project in Finland by vertical integration. Another technique which is under consideration, the United Kingdom. The British government is pro-nuclear and wants new nuclear power plants in the United Kingdom. So what the policy that they designed, and we shall see whether it will be successful or not, is a so-called contract for differences, which from a financial point of view, this is essentially a swap contract, that the British government and the nuclear investor will sign a contract for difference or swap contract, which means that every year they will swap the electricity market price and a pre-agreed strike price. So essentially, it's as if the British government signed a long-term contract for a fixed price, which of course generates a stable cash flow to the nuclear project. The third market economy where nuclear is under construction today is the United States, the Varró project in Georgia. And for the Varró project for Georgia, the US federal budget gave an $8.3 billion capital guarantee to the project. So essentially the investment is guaranteed by the US government. Now of course, if the Department of Treasury signs a piece of paper giving you an $8.3 billion guarantee on your investment, then you will find investment in the nuclear. But the key challenge is that in the past decade, and that was even before Fukushima. So very important to say that Fukushima, of course, did not help. But the key challenge to the nuclear industry came even before Fukushima, and that is the awful, absolutely awful cost inflation and project management problems of nuclear. Now, the Olkiluoto, the Finnish project that you mentioned, is 6 years behind schedule. Originally they intended to be finished by 2009. The current target is 2015. I wouldn't be surprised at all if there were further delays. And they have a 2.6 billion euros cost overrun. And that's actually not the worst. The worst in Europe is Flamanville in France. Flamanville has a 3.3 billion euros cost overrun. The Vogel project in the United States that I mentioned, they just started construction less than a year ago. They are really at the beginning of the project, and they already announced a $900 million cost overrun. So absolutely awful. Now, if you calculate, it's a very simple corporate finance calculation that you can make. That let's imagine that you build your nuclear power plant for 8 years from $4 billion. What is the net present value of that? And just imagine that you build it in 10 years from $6 billion. It's a huge, huge difference between the two. So even a small, actually the parameters I usually use, even a small project management problem, like 2 years delay, 20% cost overrun, wipes out more than 90% of the net present value of the project. So what?
Why is it like this? Why is nuclear so much different from any other construction project?
That's a very, very good question. It's a very good question. I don't claim to have a very precise scientific answer to that, but I tell you my impression. First of all, the nuclear power plants are extremely complex and very large-scale technologies. The very interesting thing is that the nuclear industry keeps talking about small modular reactors. The idea that to have smaller nuclear reactors which will be built in factories in modules. The reality is that real large nuclear power plants get bigger and bigger. So the current nuclear power plants under construction are actually much bigger than the ones operating. They are also much more sophisticated. We currently have the third generation reactor technology, which was essentially developed after Chernobyl. So it incorporates safety lessons. Now it is generally accepted that the new third generation reactor designs, they have superior safety features. So nothing like Chernobyl is even theoretically feasible in that. But the price of that superior safety is that they are very, very complex. And then comes the learning by doing effect, is that the West stopped building nuclear power plants in the 1980s. Now in the United States, the last engineer who was still a project manager of the nuclear power plant construction retired 2 years ago. So when they started the Varró project, nobody had any idea how to do it. They had to reinvent the wheel all the time. In fact, China and South Korea has a track record of building nuclear power plant projects with a much better project management than the West. And the reason for this is that China and South Korea is building one project after the other. And consequently, they now accumulated human capital, they now accumulated experience, and when they launch the next project, they know what to do. In Europe and the United States, these projects are basically a first of a kind, individually designed with very complex, very complex issues. So I must say that unless the nuclear industry gets their act together and starts to deliver projects on budget, on time, it's difficult to see how nuclear would have a bright future. Again, as I said, South Korea, China is a very different story because they have a nuclear industry which is working continuously and accumulates a lot of experience. The other country which didn't stop is Russia. I mean, Russia has 10 nuclear power plants under construction, and again they don't aim to stop. But if you take a look at where nuclear power plants are under construction today, out of the 65 projects under construction, 3 of them are under construction in competitive electricity markets. All the rest, China does not have a competitive electricity market. In China, nuclear is developed by I don't know the Chinese name, the English name is something like a State Nuclear Corporation of China. That's a huge state-owned company, very strong financial position. They have absolutely, so this idea this idea, or the idea of discussion of who will finance nuclear investment, for the Chinese State Nuclear Corporation, this is not an issue. They have the money, and to the extent they need more money, any Chinese bank will be happy to lend them. Same story in Russia as well. Russia is having a...
But if Russia is already investing in 10 projects domestically, then why would they have the incentive to invest in a nuclear project in Bulgaria? Because this is what they wanted to do.
Well, Russia is actually currently building nuclear power plant projects in China, in India, in Vietnam, and in Turkey. And you are right that Bulgaria is also, I would say, a half project. Although I must say, in the case of Bulgaria, I wouldn't bet on that project actually being built. The Chinese, Indian, Turkish, and the Indian, I think it will be built.
Do we do this through national ban?
Yeah,
Our state-owned.
Sure. Yes, I'm not, in the case, it's a different business model every time. Because in the case of China, the Chinese simply pay the bill. So they bought a nuclear power plant from the Russians and they pay the bill. Now this works if you have money. If you have money. In the case of Hungary as well, I don't know about Bulgaria. In the case of Hungary, there is a discussion in Hungary about building a new nuclear power plant, and the government would favor Russian technology. The only slight problem is that they couldn't pay the bill. And I keep telling to policymakers in Hungary that building a Russian nuclear power plant is not like the Russians will take a Santa Claus pose and bring a huge sack of money. No, you have to pay the bill. Frankly, I don't know whether Bulgaria could pay the bill or not. That's Hungary certainly couldn't. In the case of Vietnam, there's a long geopolitical friendship between Russia and Vietnam going back to communist times. So probably that deal was signed at the highest political levels between the Russian and the Vietnamese government. And frankly, nobody really knows the financial details. In the case of Turkey, it is actually Russia who invests in the equity of the nuclear power plant. So Russia is providing not only the technology but also the money. Frankly, I think it's either Rosatom or there's another Russian state-owned entity for nuclear exports. So there a Russian entity is investing in the equity of the nuclear power plant. And Russia is providing the technology for the Turkish nuclear power plant, and the Turkish government is guaranteeing the sales price of electricity. So I would say that from a Russian point of view, that's actually a very, very good project. Because they can sell their technology and they have a secure investment.
At which point of the planning of the nuclear power plant is getting rid of the nuclear waste taken into account? Is that in your calculations?
No, absolutely. And in most cases, you will have to do two things. One is you have to reprocess the spent fuel rod, and second, you have to do something to get rid of it. That something is usually finding an appropriate geological formation and you ride for 1 million years.
Who pays for that?
Pardon?
Who pays for that?
That is for the nuclear operator. That every country who operates nuclear power has to do it. Because basically, usually, if you buy a nuclear technology, usually you can also buy the reprocessing. So what happens is that you take the full spent fuel rod. For example, you send it to Russia, the Russians will reprocess it, but then they will send you back to get rid of it. And you will have the responsibility for getting rid of it. At Soviet times, the Soviet Union took back the spent fuel rods from the Eastern European countries forever, but at that time they built nuclear weapons from the spent fuel rods, so everybody was happy about it. But today, But today, some countries like France, the United Kingdom, and also Russia offer services for this repossession, for this repossession, but then they will send back the spent fuel rods, and then it is the country's responsibility to deal with it. So the standard technique for that is that the nuclear operators are obliged by their government to set aside a certain amount of money. So, for example, in Hungary, this is something like 200 billion euros per year, to set aside money in a special fund, and that special fund will have to pay for the final nuclear-based depository. Now, very frankly, whether that money will, at the end of the day, enough to build the final base depository, no one knows. That's the honest answer. So, and there is not, and right now there is not a single country in planet Earth who built a proper, really reassuring long-term nuclear-based depository. So that this is still a problem to be solved in the next couple of decades. Now, as I said, financing nuclear in China or financing nuclear in Russia is not an issue. That's because these are vertically integrated state-owned companies and the governments have money. So the only question is whether the government has a political will to build nuclear power. But financing nuclear is a big issue in the West if you want to do it from private capital. Because the projects are so huge. It's again the Germany right now has more than 500,000 investors into solar power, because the average project size in solar power is roughly 10,000 euros. So with a project size like this, you can mobilize the investments of the middle class. You don't need bank lending at all. In fact, German middle class families would invest 10,000 euros into a solar panel in their rooftop, and that will be part of their pension savings, because then it will generate an income for them. Now, compared to that, in Europe and the United States, there are less than 10, but if I want to be honest, roughly 3 or 4 companies who have the financial strength to build a nuclear power plant. Because we are talking about a 10 billion euro project size or higher. Also, you can build a solar panel in a couple of weeks. A nuclear power plant takes you a decade. And again, during that decade, energy technology can change a lot. 10 years ago, solar panels were around 5 times more expensive than they are today. And 10 years ago, we did not know about shale gas at all. So two very, very important technology shifts, solar power and shale gas, took place during this decade. And I'm reasonably sure that in the next decade, we will also have technology surprises. You know, we have these long-term projections for energy demand and the different energy technology and so on. I mean, we are 100% sure that this is not what the future will be. We are 100% sure that there will be some big technology surprises. Of course, we don't know which technology will surprise. But putting your 10 billion euros in a nuclear plant which will take them 10 years to build, and no one knows what will be the state of the other technologies 10 years from now, that's extremely risky. And in some cases,
I had a question to your previous slide. If you, it was discussed that Russia is a pretty important net exporter of nuclear technology.
Yeah.
I think even in Iran's Atomstroy export built this, or helped build this, the nuclear reactor. My question is, in the near future, is it possible that other maybe developing countries would move up so high technologically that they can become a net exporter of nuclear technology, such as China?
well, the only, okay, there is already an example for that, South Korea. You know, South Korea first launched a domestic nuclear program. They built several nuclear power plants on budget, on time. They are quite good. and when Abu Dhabi decided to build nuclear, it was the South Koreans who won the tender. Now, of course, this did not come from nothing. South Korea has a very, very powerful engineering industry. The big South Korean industrial firms can build very good oil refineries, very good power plants. So South Korea is very good in heavy industry. They could base so basically they could base their nuclear program on that. What China is doing is buying and learning at the same time. So China is building a Russian nuclear reactor, but China is building a French nuclear reactor, and China is building a Toshiba Westinghouse, that's an American-Japanese. So China is building a Toshiba Westinghouse reactor. And the typical deal is that the State Nuclear Corporation of China signed a contract with Toshiba Westinghouse, which involves that we buy 5 Toshiba Westinghouse nuclear power plants, plus you will help us developing a new Chinese nuclear power plant design, which will be based on the Toshiba Westinghouse technology, but will be Chinese. So this is you don't just sell a product in China. They always ask for the opportunity to learn from the technology. So some of the Chinese projects which are ongoing right now are now based on this Chinese designs which were developed in cooperation with the big Japanese and American firms, and they are actually quite good. Now, China has not yet sold a nuclear plant outside China, and my impression is that their designs are quite good. But with nuclear, it's not only the design that matters. It's also the project management capability that matters. It will still take some time for China to establish that project management capability. So currently the only place where this issue is seriously considered is the United Kingdom. There is a discussion about the possibility of Chinese investment in nuclear in the United Kingdom. It's an ongoing debate. Very difficult to predict what will be the decision of the British government. I must say that apart from China, I don't really see the prospect of other emerging countries really making it. India is building nuclear, and they have some domestic nuclear designs, but it's difficult to see for India as well. Again, don't forget, Russia, the Soviet Union started its nuclear program in 1942. So they have several decades technological experience with nuclear. So that's very difficult to build up. Now, in some parts of the energy system, you can bypass the problem of bank lending by attracting alternative investors, private equity investors, sovereign wealth funds from the Middle East, Japanese trading houses, and so on. Some of them works very well. So, for example, Gunfleet Sands, that's a big offshore wind farm in the United Kingdom. There the business model was that the developer company built the offshore wind farm. Now, building the offshore wind farm is actually quite risky, because these are 20-story high steel structures that you have to put them in steel into the sea. So there's a lot of project management risk. Nobody likes the project management risk, so the company developed the offshore wind farm, and once the offshore wind farm was ready and operating, then they sold 2/3 of it to a Japanese trading house, brought in the cash, and they used this cash to build the next offshore wind farm. This works perfectly. Similar story for electricity networks. RWE needed money, so they decided to sell 75% of the electricity network. Now, electricity network is a stable, is a fixed asset. It generates a stable cash flow. RWE had no money, attracting billions of euros from insurance companies, pension funds, and so on. into electricity network. But that works for everything where the technological risks are already handled, but I don't really think that would work for nuclear. So I must say I have to say that I'm not very optimistic about nuclear in Western market economies, because it would be very difficult to affect the investment. So, and that has some significant implications. So this is the red is the projection of European nuclear production in our 450 ppm scenario, the decarbonization scenario. And the blue, the current policy scenario, is a scenario in which nothing changes in politics and energy policy. And in the current policy scenario, European nuclear production is going down because you have the German moratorium, you have the Belgian moratorium, Switzerland is getting out, and a lot of European countries talking about nuclear, but in reality unlikely to be able to build. You know, frankly, for example, in Central Eastern Europe, you can go from Poland all the way down to Bulgaria, and every country is talking about building a new nuclear power plant. But if you take a look at who actually has the money and the project management capability to do it, right.
What is the role in this whole situation of European Investment Bank? Because they're somehow connected with financing of energy efficient projects.
Yes.
But I've never seen
Yes,
nuclear project.
No, because you know, in Europe, the political attitudes about nuclear power range from extremely hostile in Austria to extremely supportive in the Czech Republic. It's a very divisive issue. So it's. I'm not aware of the EIB having involvement in nuclear. I don't know, but certainly there will be a difficulty designing a European level policy on it, because you have some very pro-nuclear countries and very anti-nuclear countries. So it's not something on which it is easy to build consensus. But certainly, if you take the difference between the two scenarios for nuclear, I mean, the difference between the two is equivalent to 100,000 windmills. Now, so basically, if you want to reach the same carbon dioxide emission target without changing the baseline on nuclear, which baseline would be going down, then you would have to build 100,000 more windmills. Germany today has 22,000 windmills. Okay, so 100,000 is an awful lot. So I'm not. These guys said that we have this troika with the 3 horses where 2 is not pulling. The carbon capture and storage is not performing, and nuclear is not performing either. So the news are not very good. And the other country where it is worth comparing nuclear with renewables is Japan. Of course, Japan, since the Fukushima disaster, shut down practically all of its nuclear capacity. There are only 2 nuclear reactors operating in Japan. Japan implemented some renewable energy programs. Unfortunately, it's difficult to see how renewable energy could replace nuclear in Japan. Japan has a potential for geothermal energy and maybe solar power, but I mean, all the geothermal energy production in planet Earth, everywhere, is less than 1/3 of the pre-disaster Japanese nuclear production. And all the European solar power adds only this much. So if Japan, now, I'm very understandably, after the Fukushima disaster, the Japanese society is extremely concerned about nuclear security. This is completely understandable. On the other hand, replacing nuclear with renewables is just not going to happen. So if Japan decides to get out of nuclear, then they will probably buy huge quantities of gas. That's the most likely. That's the most likely replacement. From Australia and also from East Siberia. Now the only, I would say the only really good news in the picture is that renewable energy, primarily wind and solar power, is growing as it should. So that's the third horse. The renewables are really pulling very hard. But don't make a mistake. Renewables do what they should, but renewables cannot compensate for the other two horses, carbon capture and storage and nuclear. So if renewables do what they do, but we lose nuclear and lose carbon capture and storage, we are still in deep, deep trouble. But it is growing very rapidly, renewables are growing very rapidly, but the challenge is that the most rapidly growing component of renewable energy, the one which is progressing really well, is wind power and solar power. But whereas with carbon capture and storage you operate conventional power plants with the same method as you did, and also there is also a lot of technological experience operating nuclear power plants in the electricity system. With wind and solar power they are fundamentally different. Because because the wind is either blowing or it's not blowing, the sun is either shining or it's not shining. So the production of wind and solar power depends on the weather. Whereas in the electricity system, you need to follow electricity demand with electricity production in real life. second by second, or more exactly by millisecond to millisecond. The 50 Hertz frequency in an alternating current network means that to keep the 50 Hertz frequency, you need to match demand and supply real time. And if you don't do that, then the 50 Hertz frequency will start to deviate from the 50, and very, very soon the system will completely collapse. And by the way, having too much electricity in the system is technically at least as dangerous as not having enough electricity in the system. You know, when you have a big blackout, the political reaction is always that the politicians conclude that we don't have enough power plants, we need to build more power plants. Now actually, in 2003, when there was a huge blackout in the eastern United States from New York to all the way to the middle of the United States, there the problem was too much electricity in the system. So when you have too strong wind or too much sunshine, that can also cause an extremely serious technical problem in the electricity network. So managing an electricity system with large proportions of wind and solar power, and in some European countries this is really large, is a formidable technical challenge, and basically means that the 100-year-old system operation paradigm of the electricity system will need to be completely transformed. In Europe, for example, the amount of new wind and solar is just phenomenal. You know, the red is the existing gas-fired power generation, wind and solar in Europe. So in Europe currently you have an awful lot of gas-fired power generation, some wind, some solar. Gas-fired power generation is really good in this respect because gas-fired power plants are extremely efficient and extremely flexible. So gas-fired power plants are very well suited to manage the volatility in the electricity system because they can adjust their production up and down very quickly and very smoothly. Now, in a situation where you have a lot of gas, some wind, some solar, everyone is happy. But by 2035, we will actually have more wind power generation in Europe than what we have gas-fired power generation today, and even solar will be catching up very, very rapidly.
Does it mean that by 2035 the European Union will not produce electricity by gas at all?
Well, it will. It will.
According to this,
it will. But it's because you need gas-fired power generation. With a bit of a simplification, imagine a cold, dark, still evening. There's no wind, no sun. In those evenings, gas-fired power generation will have to run flat out to supply electricity because you cannot tell people that tough luck, no energy today. So Europe will need a lot of gas-fired power generation, but gas-fired power generation will only used in in periods when the wind is not blowing, the sun is not shining. And to illustrate this change, in a traditional electricity system, you have let's say there's 8,640 hours in a year, 365 times 24. Out of this 8,640 hours, let's say a nuclear power plant would operate 8,000. You operate it day and night, and you stop for maintenance and safety reviews and so on, but let's say 8,000 hours. A coal-fired power plant would operate, let's say, 5,000 hours. A gas-fired power plant would operate, let's say, 3,000–4,000 hours for the midday periods. That's the conventional system. Now, in this new system, we might have nuclear or might not in Europe in the future, we shall see. But gas-fired power plants, instead of 3,000 or 4,000 hours a year, will operate only, let's say, only 1,000 hours a year, because they will operate only when the sun is not shining or a wind is not blowing. In the case of Germany, they will probably operate in the evenings, because peak electricity demand in Germany is at 7 o'clock in the evening in December, which is a bit challenging because the sun sets at 5 o'clock in December in Germany. So there's precisely zero sunshine in Germany, exactly at the time that people use most electricity. So in Germany, in winter evenings, gas will operate a lot. But for example, during the summer, in a summer, you could have several weeks in the summer when gas-fired power plants will not operate at all, because you have wind and you have sunshine during the day. So their operations will be completely different. Overall, they will produce much less. So this will go down to this, let's say. But they will still play a crucial important role.
Is it possible to accumulate this energy technically from wind and solar plants?
Today, the only practical technology to that is pump storage hydro, which basically means that when you have too much electricity, then you use water pump to pump up water to a reservoir, and then you need the electricity, then you use it as a hydropower plant and generate electricity. So this is very good. The tough luck is that it's high school physics to calculate how much water you need to store energy, and that's a huge amount of water. So basically these pump storage hydro plants are large artificial lakes in high mountains. And in Europe, basically Switzerland and Austria has the proper geography for that. Building large energy projects in Switzerland or in Tyrol in Austria, where you have to fight with every restaurant owner and every ski resort and so on. That's not easy. Scandinavia is also not bad. So these hydro plants in Scandinavia and Switzerland, they will play an important role. Another very interesting thing is that in southeastern Europe, basically Serbia, Bosnia, Romania, Bulgaria, the geography is also quite well suited for building pump storage hydro plants. And there I think the licensing issues should be more manageable. But of course, for that, today the electricity network in southeastern Europe is extremely bad. So even if you have proper hydro plants in, let's say, the Carpathians in Romania, there is no way to bring the electricity from Germany or to Germany. So that will be, the network will be another big issue. And the other electricity storage possibilities are in a very infant stage. So one possibility is electric cars that people will plug in their cars, and the cars. So the theoretical concept is that every car will have an onboard computer, and when you park your car, the car will be plugged in, the onboard computer will communicate with the electricity system operator, and when the wind is blowing strongly and there is a lot of wind power, then the car will take the electricity from the grid, and when the wind is not blowing, then it will stop taking. That's a theoretical possibility, but we are not yet there. And the third theoretical possibility is hydrogen, that you can produce hydrogen from water with electricity, and then you can produce electricity from hydrogen in a fuel cell. Unfortunately, with the current technologies, the efficiency of this process is very bad. So you produce hydrogen from the water with electricity, and then you produce the electricity with the fuel cell, and you get back something like 1/3 of the original electricity. Everything related to hydrogen is extremely expensive and difficult. Storage of hydrogen, transportation of hydrogen, and so on. So today the only thing that works in practice is pumped storage hydro. Electric cars might work, let's say, 2020 if you like. There was a question somewhere there. Somebody. No questions. Good. Yes. Now, for the other problem is that the renewables are not driven by the carbon price. Renewables are driven by state-driven renewable policies. As a result, the location of renewable investment in Europe is not determined by the geographical factors. You don't put your wind turbine when the wind is blowing strongly. You put your wind turbine where you get good state subsidies. And the same for solar power. If you drive, let's say, from Vienna to Budapest, you will see huge numbers of windmills in the Austrian side because the border to Hungary, and it stops. Now, believe it or not, the wind does not stop at the border. But what stops at the border, that in the Austrian side you get Austrian subsidies, in the Hungarian side you get Hungarian subsidies. The Austrian subsidies are much better, so everybody invests in the Austrian side. The same with solar as well. That's why you have huge quantities of solar power in countries like Germany, which are not funny at all. Because the investment is distorted by the subsidy schemes. But it is big. It is really big. Last year, 5% of the investment in the German economy was solar power. Not investment in the German energy sector, investment in the entire German economy. Around 20% of all the imports that Germany imported from China were solar panels. China is producing most of the world's solar panels, and they are exporting huge quantities of that into Europe. So renewable energy is really growing rapidly, and especially when you have a situation where European demand is very weak because of the Eurozone crisis, it's rapidly taking place. Now, the idea, one very popular idea in the renewable industry, that if you have a large enough system, a very, very interconnected system, then this weather-related volatility will be handled because statistically, maybe you don't have wind in Germany, but you have wind in Poland, or you have sunshine in Spain, and the statistical volatility of the entire system will be smaller than in an individual country. Now, this is true, but this is not enough, unfortunately. So this is how I would say an optimal European renewable system would look like, which is, with a bit of a simplification, would be 40% solar power, 60% wind power. So if you run the time series analysis of what would be the optimal combination, we should have the lowest volatility. That would be around 40% solar, around 60% wind. But even that combination would have huge volatility. And the red is the electricity demand. So you would have periods like this, then you have much, much more electricity than what you need. And periods like here, then you have much, much less electricity than you need. So simply relying on geography does not solve the problem. For example, in Germany, there are around 1,000 hours a year. So that is equivalent to something like 3 hours a day, 3 hours every day on average. Then there is no wind. Now, if you take those hours when there is no wind in Germany, the conditional probability of having no wind in the United Kingdom either is around 50%. So during the time that there is no wind in Germany, around half of those times there is no wind in the United Kingdom either. And this is really, really bad news because these are the two countries which are investing in wind power most heavily. So this weather-related volatility, that geography alone does not solve the issue. I already mentioned the pump storage hydro, which will play an important role. But and I also mentioned that the gas-fired power plants, their ability to really rapidly ramp up production and ramp down, that's also hugely important. But we will also need demand-side flexibility. So today people consume as much electricity as they want at any time of the day, basically. In the future, we will need smart electricity pricing. So just like in mobile phones, there are 100 different packages for mobile phones, tariff packages, and the same mobile phone conversation can cost you 10 times as much as another one, depending on whether is the peak hour or not a peak hour, and depending on what type of package you choose. So this is the future of electricity supply, that we will have to have much more adjustments on the demand side as well, because having an awful lot of wind and solar power and always supplying a very rigid demand, that's going to be very, very, very difficult. Now, the other big challenge will be the electricity network. Because today, when we transport energy, we mainly transport energy in the form of oil and gas, the high energy density primary fuels. And as a result, the energy transportation capacity of the oil and gas pipeline network exceeds the capacity of the electricity network by a factor of 10 or more. Just an example, Germany has an undersea pipeline running from Russia, that's the North Sea pipeline, and Germany also has an undersea electricity cable running from Scandinavia, the Nordberg cable. Now, if you decided that you want to burn the gas in Russia, turn it to electricity, and transport the energy to Germany in the form of electricity, you would need 15 electricity cables running under the Baltic Sea to substitute for the one gas pipeline. The pipelines are just incredibly efficient to transport energy. Electricity transmission lines transport much, much less. So this was a modeling that was done of how a perfect European electricity transmission system would look like if Europe completely moves to renewable energy. Now, the big challenge is that if you move to renewable energy, you get rid of oil and gas, you go for solar and wind. For solar and wind will generate you electricity, and consequently you will have to transport the energy in the form of electricity. And you can no longer use pipelines. Now, the thick red line, one thick red line here represents 20 kilowatts of transmission capacity. Now, with a bit of a simplification, on a high voltage transmission line is roughly 1 kilowatt. Okay, so a thick red line is 20 high voltage transmission lines running parallelly to each other. And you see the number of thick red lines all over the place. This is not going to happen. No way. Two things will happen. One is that we need to apply very, very smart technology to improve the transmission of a given line. There are some technological possibilities for that. Oh, and by the way, I could have put a map of China here as well. I actually got such a picture from our Chinese colleagues, because if you imagine a map of China here, then you will see electricity demand in eastern China, let's say from Beijing all the way down to Guangdong, and unlimited quantities of wind in the north, unlimited quantities of coal in the west, in Xinjiang, and unlimited quantities of hydropower potential in the southwest, in the Himalayas, and thick red lines in the map of how much transmission China needs to build in order to bring that to the eastern regions which consume the energy. So this electricity transmission is a huge challenge, not only in Europe, also in China. So one thing